Not all semiconductors are created equally. Most of these essential little switching devices are built into everyday electronics like phones, cameras and computers, where they turn small amounts of power on and off. A high-power ABB semiconductor has more fun. Imagine a switch no bigger than your little fingernail that turns power equal to a Formula One racing car on and off thousands of times a second. Chip quality is paramount, so ABB makes its own semiconductors, and in 2010 added new buildings and manufacturing lines to its semiconductor factory in Lenzburg, Switzerland. A speck of dust, 1/1000th of a millimeter wide, can affect chip quality, so the workplace is kept cleaner than a hospital operating room. Air is filtered, temperature constant, and vibration minimized. To eliminate contamination, assemblers wear protective clothing, hoods, gloves, face protection, and special shoes. Manufacturing high-power semiconductors is a precision business. As many as 300 separate production steps are needed to make each chip. They end up in very special applications where large amounts of power must be reliably switched in fractions of a second. For example, billions of chips are used in high-voltage direct current (HVDC) power transmission and distribution systems to transport electricity over long distances. They are also key components in locomotives and industrial drives, help stabilize power for large aluminium smelters and cement plants, and connect renewable energy sources like wind and solar to power networks. High-power semiconductors will play a key role in developing smarter, more reliable power networks.
Assalamualaikum warahmatullahi wabarakatuh. Our topic is about metal semiconductor energy band diagram. So, my name is Megat Ali Fahmi bin Muhammad Aziz with number metric 192185. I'm gonna explain about the introduction of metal semiconductor energy band diagram and a little bit about the application of metal semiconductor energy band diagram.
Assalamualaikum. I am Muhammad Nasif Uluan bin Abdul Wahab. Number metric 192316. So today I will talk a bit about the thermal equilibrium energy band diagram and also reverse bias and forward bias energy band diagram.
Hi, my name is Muhammad Fakin Izzat bin Muhammad Asri. My metric number is 192299. So in this video, I'm going to explain about a few questions and solutions that may be asked in this topic. Hope you enjoy the video. Thank you.
Bye-bye.
Hello, so I am Megat Ali Fahmi. I will explain about metal conductor energy band diagram. So if you don't know yet what is actually a band diagram is, energy band diagram is a diagram that plot various key of electron energy level. As you can see the example here, you can see my cursor. This is the conduction energy level. This is the Fermi energy level. And this is the valence energy level. This is the three example that I can show to you, and this is obviously the energy band diagram of semiconductor because the Fermi energy is a lot closer to the conduction band, and this is metal energy band diagram because it have a very far Fermi energy to the vacuum. So next I will explain to you about the concept of work function. Work function is actually the energy needed to electron to be removed from the solid point, which is here, to the vacuum point, which is here. So this is, we can measure the work function of the metal by, you can see here, this from solid state to the vacuum level, and for semiconductor from this to this. the vacuum level for metal and semiconductor is the same. So next I will explain to you what will be happen if we brought together the metal and semiconductor here. This is what will happen. Firstly, the Fermi energy of the metal and semiconductor will be the same, and the semiconductor will lose its electron as actually the semiconductor have a higher Fermi energy here, while metal have a lower Fermi energy. So if we brought together, the electron here will drop to metal, so it will reach the equilibrium state. So what will be happen to the energy level of conduction, Fermi energy and valence? So next, the conduction energy level will be more far away from the Fermi energy level. As you can see here, it getting far away, while the valence energy level will be a lot closer to Fermi energy level, as you can see here. And starting from this line, there will be a depletion region from this to this here. I think that's all for the introduction. Thank you.
Hi, I'm Nasir. Now I'm going to explain about the condition of the metal semiconductor band energy band diagram in thermal equilibrium, and also the condition in the forward bias and the reverse bias. So as we can see here, this is not a thermal equilibrium diagram, because what the Fermi energy level of metal is differ from that in the semiconductor, so they are not in the same level. So in thermal equilibrium, electron in the n-type semiconductor can lower their energy by transversing the junction. As the electron leave the semiconductor, a positive charge due to the ionized donor atom stay behind. So this charge create a negative field and lower the band edges of the semiconductor. Electron flow into the metal until equilibrium is reached between the diffusion of electron from the semiconductor into the metal and the drift of electron caused by the field created by the ionized impurity atom. So as what I say, this equilibrium is characterized by a constant Fermi energy throughout the structure. And now for the under forward bias condition, we will apply positive voltage. So the Fermi energy of the metal is lower with respect to the Fermi energy in the semiconductor. Okay, this result in smaller potential drop across the semiconductor. The balance between the diffusion and drift is disturbed, and more electron will diffuse toward the metal than the number drifting into the semiconductor. This lead to a positive current through the junction at a voltage comparable to the built-in potential. And for reverse bias, we apply negative voltage. So the Fermi energy of metal is now raised. You can see a height difference between forward and reverse bias. So it yield a larger depletion region. The depletion region also increase, become wider, and larger electric field at the interface. the barrier which restricts the electron to the metal is unchanged, so that the barrier independent of the applied voltage and limits the flow of electron. The metal semiconductor junction with positive barrier height has therefore a pronounced rectifying behavior. A large current, so in the conclusion, a large current exists under forward bias, while almost no current exists under reverse bias. That's all.
Hi, I'm Izzat. So we are going to see a few examples of the questions of the topic energy band diagram. Answer the following questions about a metal silicon MS junctions. We have to assume a hypothetical metal with a work function of metal as 4.60 electron volt. Assume that the electron affinity of silicon is 4.03 electron volt. We also have to assume that the silicon is n-type silicon with n donor is 10 to the power of 17, and draw an energy band diagram. Also indicate the Schottky barrier high on your sketch. So here is the solution. We begin with the energy band diagrams of the metal and the n-type semiconductor before they are connected. So here is vacuum level, and this is high of the work function of metal, which is 4.60 electron volt, and this is electron of Fermi energy of metal, and this is electron affinity of the silicon at 4.03 electron volt before the electron conduction band and electron valence band. So for the energy Fermi for these energy band diagrams, we have EFS below the energy band conduction. The precise location of the Fermi level in the semiconductor would be determined by solving this equation. For the electron node and n donor is equal to this equation. For this equation, we see that the Fermi level in the semiconductor is above the Fermi level in the metal. So when brought together, electrons will flow from the semiconductor to the metal. The energy band diagram will have a constant Fermi level, and the conduction band will bend up near the junction to show electron depletion. The valence band must be parallel to the conduction band. Far away from the junction, deep in the semiconductor, it will look like it did before the two materials were connected. Here is after metal and semiconductor is connected. Here is field-free vacuum level, and as usual, the work function of metal and the electron affinity of the silicon, and work function of barrier. This is electron Fermi metal, A Fermi energy, and this is conduction band and valence band. This is the diagram after the metal and semiconductor is connected. Next, assume that the silicon is p-type silicon with
An acceptor is 10 to the power of 17 and draw an energy band diagram. Indicate the Schottky barrier on your sketch. We begin with the energy band diagrams of the metal and the p-type semiconductor before they are connected. This is before they are connected. So here is the metal and the vacuum level. This is the work function of the metal. In this case, the Fermi levels in the separated metal and p-type semiconductors are close. So let's figure out exactly which one is higher. By using the equation, we just put in the constant value and so on, and then we got the value here, 0.135 electron volt. So that is a few example of questions that may be asked on this topic. That's all from me. Thank you.
This is how actually solar cell generate electric. That's all for me. Thank you. Next, I will explain about the application of the metal semiconductor junction, which is solar cell. Solar cell is actually the PN junction with a very large surface area. The N-type is made with a very thin layer to allow the light to pass through it. Next, the photons, which came from the light sources such as sun, will enter into the depletion region. Why the photon enters the depletion region? This is because depletion region is where the generation of electric current happens. It happens inside the depletion region. Next, the photon, which is absorbed by the atom of the PN junction, will absorb through the N-type of the metal semiconductor junction. Then the electron from the photon will dislodge, which is creating the free electron and hole. Next, the electron and hole actually have enough energy to jump out of the depletion region. Next, if we connect the wire from the cathode, which is N-type, and connected it to the anode, which is P-type, the electron will flow from cathode and to the anode. As we all know, electron actually have a negative charge and P-type have a positive charge. So the flow of the electron will create a current flow. Next, it will enter the P-type of the junction and then combine with the hole and restoring the electrical neutrality. This is how actually solar cell generate electric. That's all for me. Thank you.